Okay, so good morning, everyone. So welcome to the lectures of 2301. And today we are going to talk about a new topic, linear systems. Okay, so the rough structure of this chapter is, first we will talk about matrix norms and vector norms, condition number, stability, and then we're going to talk about LU factorization. So essentially, you take a matrix and you decompose it into a lower triangular multiplied with the upper triangulars. And we will, show you why we need this LU factorization. And then after that, we're going to talk about Cholesky factorization when you have a symmetric and positive definite matrices. Okay, so now linear system, you will see it everywhere. Okay, so in statistics, in linear regression, least square approximation. So we will do a little bit of least squares approximation in the next topic. Okay, and then in year 3, year 4, if you do applied math, you might use linear system when solving partial differential equations by numerical methods. Okay, or like in signal processing if you're doing electrical engineering. So now let we start with a very simple example. Yeah, so now I just take two matrices. Okay, so and you just take the simplest matrix you can have. What is just 2 by 2 matrix? 1, 2, 3, 4. Okay, so this is a seamless 2 by 2 matrix you can get. Well, I mean, for 2 by 2 matrix, this is a simple matrix, and then if you just take the last entries, you add on a tiny number, 10 to the minus 10. Yeah, then now which of the two computed solution, x1 or x2, which one is less accurate? So in other words, which matrix give you a good solution and which matrix give you a bad solution? Or how do you tell which matrix is a good matrix and which matrix a bad matrix in terms of numerical computation? So any guess? Any guess? Any rough guess which matrix is a good matrix? B, because the 10 to the 10, A is more accurate. But why? B is a bad one. But why? Why that is a bad one? Just because of the 10 minus 10, you say that is why? Because of the 10 minus 10 is a bad one. Plastic cancellation, no, not cancellation, no. I mean, we didn't minus anything here, so you see, the whole point is we don't have enough tools to say anything about the two matrices. Okay, so you are given two matrices. You cannot say that, okay, because 10 minus 10 is a bad number, so that therefore B is a bad matrix. I mean, it's not a scientific conclusion, right? So somehow we need to be a bit more precise. And before, I mean, we can make a precise statement, let me introduce some tools, yeah, some mathematical tools. So then first we have to define a norms. So what does it mean by a norm? Okay, you will see later on how we use it. But now let me do step by step first. Yeah. So a norm is just a way you quantify a vector by a number. Okay, so give me a vectors. Yeah. Then how do you quantify a vector by a number? So think about a vector is like a vector in R2 on the plane. So how do you quantify a vector on the plane by a number. Yeah, take the length. Okay, so take the length. Square root a square plus b square actually is a length of the vector. And more general, you know, we define the concept of a norm. You see, the norm is a function that take a vector and give a number. Okay, and then it has to satisfy the three properties. First, it has to be greater or equal 0 for every vector. And then secondly, if you have a 0 vectors, then the norm equals 0. And if the norm equals 0, it has to be a 0 vectors. So you see, and the last one is, well, not the last one, but the third one is if you take a scalar, you multiply the scalar to the vectors, yeah, then you take the norm, then it's the same as you take the scalar, take absolute value, and you multiply with the norm. And then the last one will be the triangle inequality. So you see that when you take, should be a V, not an X. It's a typo. Okay, it's very good catch. Yes, sorry about that. Should be a V. Yes, thank you about that. I will fix the typo. Very good catch. So typo, yes, I will fix that. And the last one is the triangle inequality. So you see that is exactly, you know, like what you expect if you take the length to be the norm, right? The length of a vector, then it satisfies those four properties. Okay, so V plus W is, you know, when you have a triangle, then it's the size of the triangle, then take the length, it has to less than the sum of the two other sides. Yeah, but you know, the length is just one particular example of the norm. You can have other way to define the norm as well. So another way to define the norm is, in more general, is you take the by the way, the length of the vectors, you know, could be an Rn. Yeah, in R2 you just have two components, and R3 you have three components, but you can have nth component in Rn. Okay, so we don't have to worry about the dimension in mathematics. So it could be n dimension. Then, you know, if you take square root a square plus b square, then how about if you replace the square by the power p? You take all the components, you raise to the p, and then you sum it up and you take power 1 over p. Okay, so in this case, then p has to be 1 less than or equal, I mean greater or equal 1, and then less than infinity. Okay, and we call it a p norm. And then the infinity norm. Okay, so infinity norm will replace the sum by the maximal. So if you take the maximal of the absolute value of all the entries, then you have the infinity norm. Okay, so you can show that those norms satisfy those four properties. Okay, it's an exercise. Yeah, so we just assume that it's correct. Yeah, so now suppose that I have a vector 3 minus 1 4, then what is the v norm for p equal 1, p equal 2, and p equal infinity? So now, so let me just do a quick calculation. Yeah, so now if I do a quick calculation here. So remember, you have v, well, I cannot do bone face, so I have to draw. We go underneath. Okay, so it's like a vector. So then the three component is 3 minus 1 and 4, right? Then you can see that if I take the one norm, okay, so the one norm, then it just equal, you know, the absolute value of 3 plus absolute value of -1 plus absolute value of 4. And you sum it up and then you raise to the power 1/1. So what is just the sum? Yeah, so you got 8. Okay. And then what is the infinity norm? So infinity norm, you just take the maximal value of absolute value of those 3 components, right? So max of 3, 1, 4. Okay, so this is absolute value. So what is just 4? Okay, and the 2 norm. So now this is the Euclidean norm. So it's another name is Euclidean norm. So then the the 2 norm is just 3 square plus 1 square plus 16 square. Plus 4 square. Yeah. So and then take the square root. Okay, and you take the square root. So then this one give you 9, 9, 10, 10, then 16, so 26. So take the square root 26. Then you get some number. Okay, so that is how you compute the norm. And then now I go back to the slide. So this one maybe you've seen it before. So now there is interpretation. So the 2 norm is the same as the Euclidean norm. So what is essentially the length of the vector? Okay, and the 1 norm is also called the Manhattan distance. So Manhattan is, remember, is the CBD of New York, right? So, and if you've been to New York, you will see that the street in CBD of New York in the central business district, New York, look like a chessboard like this. Okay, so on the street are parallel and it's like a grid. And then if you want to go from A to B by a taxi, then you cannot go by a straight line. Yeah, but you have to go through a line that parallel to the grid. Yeah, and when you sum it up, the sum of all the length go through the street, then it will be the 1 norm. Okay, so the green line is the 2 norm, and the purple line is the 1 norm. Okay, so in MATLAB, remember in the lab I show you that you can take the function norm of a vector x, and then if you don't put anything, that is a 2 norm. Then if you put p is 1, give you a 1 norm. Put infinity, give you infinity norm. Okay, so now we go back to the example. Okay, so now suppose that I have now I have a concept of the norm already. Okay, now can you compute? You see, now I have a vector b, right? B is the right hand side. Okay, 1, 2, and then I have a perturbation of b1. So think of a vector b, then you get some noise. Noise is like suppose you measure the voice, the sound of some by some microphone, and somebody hit a hammer outside, then it creates some noise. Okay, so the noise is the perturbation of the signal. And then you try to solve the linear system. Maybe you want to modify the signals, like make the noise of the cat become the noise of a dog, for example, and you try to solve it by a linear system, just for example. Okay, and see, now suppose you solve it. Yeah, so you take A, you solve for ax equal b, and then you do the same. Now if you take a perturbation of the vector b, it's a vector b1, you get x1. Okay, then you do the same thing for the matrix b. Yeah, and then now you compare the relative errors. Okay, So the relative errors is x1 minus x over x, the two norm. So what is the relative errors when you introduce the noise into the vector B? And this is the relative errors of the vector y, y1 when you introduce the errors in the matrix B. And then, so I say that you go to the Google form. So if you go to the Google form, they ask you, a question. So let me go to the Google form. So now if you have MATLAB, so please do this, yeah. And then I think the Google form is in Moodle. So if you go to Moodle, so you see that now we have a concept of the norm. So we have to use it, okay, to see what matrix is a good matrix. And so now let me go to the Google form. So if you go to Moodle, you go to interactive Google documents, and there is a Google form good and bad matrices. Okay, so you see it. So now I can share what is the Google form, yeah. So you have to do it in order to see the point of the next slide of the lecture. So you have to. So let me show you the form. Yeah. So now I stop the slide. I share you the screen here. So have you found this form? So let A to be a matrix 1, 2, 3, 4. Okay. So B is the 1, 2, and 2, 4 plus some small number. Okay, so which one is less accurate? Okay, so when you are doing it, let me show you how I do it in MATLAB. Okay, so I can show you what I'm doing in MATLAB. So let me share my MATLAB. Okay, so now, so remember I have vector, sorry, I have two matrices. A is 1, 2, 3, 4. Okay. And then I have the matrix B is 1, 2, 3, 4 plus 10 to the minus 10. Yeah, so I have two matrices. Then I have, the vector B is just 1, 2. And the perturbation of the vector B is B1. It's just B plus some noise. Yeah, so this one is the noise. Okay. And now remember, I solve X to be A backslash B. Okay, and X1 is A backslash the perturbation of the vector B. Okay, and I do the same for Y. Yeah, so Y is B backslash little b, and Y1 is B backslash B1. Okay. And now I compute the relative errors. So now I have the norm, right? I have the norm. So remember the norm is the one we just introduced, and we can use the function norm. And now we compute the relative errors. So x1 minus x. So x1 minus x divided by norm of x. Okay. And then norm of y1 minus y over the norm of y. So there's something wrong. Okay, so everything is okay, right? So now let me run it. So run. So it asked me to name it. So now let me say that this one is example for in the lecture notes. Yeah. So if I run it, so you see that no, something is not correct. All right, give me the same number. So 1, 2. So let me check. So 1, 2, 3, 4. Yeah. So 1, 2. Okay. So no, sorry. This one is not 3, but this one is 2. So 1, 2, 2, 4. Yeah. Okay. And now you run it. Okay. So now you can see that. Yeah, the second, yes. So is this correct? Yeah, I just corrected. So this one is 2, 4 plus 1. So you can see that the relative errors in X, okay, is about 7%. Yeah, but the relative errors in Y when you introduce the noise is 10 to the 8. Okay, it's 100 million. And so you can see that this one is the evidence that say the matrix B is a very bad matrix. Okay, so even for a very small matrix 2 by 2, if you try to use a matrix B, then it's a very bad matrix numerically, right? Because when you introduce, you see, when I put errors X error Y, I got the, sorry, how do you compute the errors? You mean like the first one, you got a different, so you got a different error. So which one is the small one? Yeah, so the big errors corresponding to what? I mean, the big errors corresponding to the matrix B, yeah? And it's okay. I mean, the matrix B produce a bigger errors, then it's okay. I mean, it doesn't matter the order, but if it's corresponding to the matrix B, produce a bigger errors, then it's okay. Okay, but essentially, you have evidence. You have evidence to say that the matrix B is bad numerically. Okay, once you compute the relative errors by the norm. Okay. So now we go back to the slide. So now how do we do it even more precisely? So now let me go back to the slide. Yeah? So you see the idea that we have to have some some tools in order to quantify good or bad matrices. So now we introduce a further tools. Yeah. So here's a norm of a matrix. So maybe for the norm of a vector, you've seen it before, but norm of a matrix, maybe you haven't seen it. So before I talk about the definition, let me go and introduce the pictures. Okay. So maybe this is easier to explain by pictures. Yeah. So let me share the whiteboard. So now let me clear everything now. So you see, suppose just take R2, okay? And suppose we take a matrix A just some A, B, C, D. Okay, so A, B, C, D are real numbers. Okay, so now suppose I take a circle. So this one is like a unit circle, right? Then maybe I take everything inside the unit circle. So I take all the vectors inside the unit circle. So suppose this is a vector in the unit circle. Yeah, so any vector in the unit circle, and then I map it. So this one is a vector x. Yeah. Then I map it by the matrix A. So then this one is AX. So maybe I got some AX here, yeah. Okay, so my question to you is, suppose I take every point in the unit circle and I map it into the range of the linear transformation. Then what is the pictures? What is the pictures of the range? What pictures do I get? So what pictures do I get here? Anyone? The ellipse, yeah, it's correct, yes. It will be an ellipse, and the ellipse will center at the origin, okay? I mean, suppose you just take like a very simple case, suppose I just take a diagonal matrix, yeah? So you got A here, and you got D here, and 0, 0 here, okay? Then, then you get a ellipse that is somehow amplified by a factor A in the x-axis, okay? And then amplified by the factor D in the y-axis. So that is that is the image, okay? But in general, I mean, it can be in any direction. Yeah, so it can be in any direction. So then the norm of the matrix. So the norm of the matrix will be the radius of the ellipse. Okay, so that is the explanation. I mean, the illustration of a norm of a matrix. So now I go back to the slide, and you will see that suppose I take. You see, suppose I take a matrix A to be 1, 2, 2, 2. Okay. Then I plot the range of AX when X is in the unit circle, and I got an ellipse like this. Okay, I got an ellipse like this. It's a very, very thin ellipse, but I mean, it's still an ellipse. And then if you take the radius of this ellipse, okay, and the radius of the red set, then it's the norm of the matrix, the two norm of the matrix. Okay, so that is the rough illustration of the two norm. So now we go back to the formal definition. So the formal definition say like this. So the norm of the matrix, okay, is the maximal radius, okay, AW, and you take the norm, okay, and this one could be any norm, yeah, and W come from the circle, right? Because inside the disk, I mean, it is smaller than outside, I mean, on the boundary. So we just, it's enough to take only on the circle, and you take the radius of the ellipse, okay? So it could be in any norm. So now y is equal the second expression here. Well, so this one, let me show you why it's the same, yeah? So now let me go back to the writing. So maybe it's similar to write by pen. Okay, so now what I have is A to be max of, Do you see my handwriting? Yeah. Okay, so max of AW over W, take the norm, and W is on the unit circle, right? But now you see, now if I claim that it's the same as you just take AW, okay? Well, maybe we use a different letters. Maybe we use AV. AV, yeah. You take the norm and you divide it by V. Okay, provided that V is not a zero vector. Yeah. So why is that? Again, so now if I take, so remember, if I take V is a vector. You can write V as, you know, V divided by the length of V, right? Multiply by the norm of V. So divided and multiply by the same thing. Yeah?
Hi, could you refocus the camera? It's a bit blurry for us.
Okay.
Thank you.
So how do I focus? Is it better now?
Yeah.
Okay.
Thanks.
Okay, so if I let V to be V divided by the norm of V and multiplied by norm of V, then it's still the same, yeah? And then I say that, okay, I label this to be W, okay? So this one will be labeled as W multiplied by the length of V, yeah? Then now I can write, you know, now I can write max of, so instead of AV, yeah, now I write AW, you know, multiplied by the norm of V, right? So I just replace, remember, I just replace here, yeah, and divided by so the V, right? So I write W and the V inside. Okay, but remember the so now instead of maximum over V, right? I say that maximum over W, and now the length, I mean the norm of W is just equal 1, right? Because you can see that if you take the norm of W, then it's just equal 1, yeah. And you can remember that the norm, right? When you multiply by a scalar, you can pull the scalar outside. You can pull the scalar outside, so it's become max of W equal 1, and you pull out the scalar outside. So V, the norm V is a scalar, so you got outside. And then the same here. W. And remember, V is a non-zero vector, so you can cancel this. Okay, so then you get exactly the first equality. So the two the two definitions are equivalent. Okay. So that is the definition of the norm of a matrix. Yeah. So is it okay now? So can you have so Y? Yeah. So W is a unit vector by design. Yes. So that's why the norm of W is 1. Yeah. Because we take V over the norm of V. So that's why the norm of W is 1, right? because otherwise you can just take so W here. Okay, so W is V over norm of V, right? So this means that the norm of W is just equal the norm of V over the norm of V, which is equal 1. Okay, so does it explain? Does it explain you? Okay, so now we stop. Okay, the writing and go back to the slide. And now you can see that, okay, now you have the definition here doesn't depend on the norm. Any norm is okay. So you can use the 2 norm, infinity norm, or the 1 norm. Okay, and you get this. And you don't have to restrict yourself to R2. You can have an Rn and can be any dimension. So this picture is only valid for the 2 norm of R2. Okay, so R2 on the plane. But you know, like in R3, this one become ellipsoid, and in R4 it's become you know, some hyper surface in the 4 dimension, but it's still ellipsoid. Yeah. So now my claim is that the norm, okay, is the smallest constant C, so that if you take AV, you take the norm, then it less than or equal C times the vector V. So why is that? Well, so now you go back to the definition. Yeah. So now suppose I have so I go back to the piece of paper. So now suppose I have AV. Okay, take the norm, yeah, less than or equal CV, yeah. Okay, then now you can divide it by V. So assume that V is not a 0 vector. So you divide it by V, I mean the norm, yeah, less than or equal C. Okay. But now if you take the maximal over on the vector V, non-zero. Yeah. Then it's still less than or equal C. Okay. And this one by definition, this is a norm of the vector A, sorry, of the matrix A. Yeah, less than or equal C. So this is another way to say that the norm is the smallest constant C, so that this inequality happen. Okay, so the C, you know, suppose C is any constant, right? That, you know, satisfy this inequality, then the norm of A is the smallest constant that satisfy that. Yeah, so that's what it's saying. So now if you go back to the slide, so what is the max notation? Can I move my paper up? What does the max notation mean? Max is mean like you take the maximal of this quantity over all the vectors V non-zero. Okay, so max, is it because V can be any vectors? Okay, can you see it now? So V can be any vectors. You take, and this quantity is a real number, right? Changing depends on the vector V. So you just you take the maximal single entry. No, you take the maximum over the set of all vectors non-zero vector V. So remember, this is a single number. I mean, it's just a real number, right? Because you have a matrix, you have a vector, you multiply, you get a vector, then you take a norm, then you get a number. And here you have a vector, you take a norm, you have another number. So this number over this number is still a real number, right? And then you vary V over the whole Rn. So for all the vectors, V non-zero vectors. Yes. Yes, something like that. Yes. So you evaluate AV over V for all possible non-zero vector V. Does it make sense? So suppose in R on the plane in R2, right? Then you take all possible vectors in the plane except the origin, because the origin is a zero vector. So does it make sense? Yeah. So you see the concept of matrix norm somehow doesn't depend on the vectors, but it depends only on the matrix A only. Yeah. Okay, so now we go back to the lectures. Yeah. So so now, you know, there are properties that the matrix norm satisfy, and we skip the proof, but essentially the norm of a matrix greater or equals 0, and you can pull out the scala, and if it's a zero matrix, then you got a norm equals 0. If a norm equals 0, you got a zero matrix, and it satisfies the triangle inequality. Okay. Okay, so now we consider two special cases. Okay, so the one norm of a matrix can be computed by taking the maximal absolute column sum. Okay, and the infinity norm can be computed by maximal absolute row sum. So this is the theorem. Okay, so the theorem is a consequence of the definition. It's not a definition of the one norm, but it's just a consequence. So how do we prove it? So let we prove the cases for the one norm for the simple case. Okay, for only for the 2 by 2 matrix, and you can have a general proof in the lecture notes. So now let me go to the piece of paper. So now suppose I have a 2 by 2 matrix. I have a 2 by 2 matrix like this. So A, B, C, D. Okay. So my claim is A1. I mean the one norm of the matrix A. Okay. So it just equal max of, so just take the absolute value of the column. So A plus C. Okay. And B plus D. Okay, so that is the theorem. So now how do we prove that? Okay, so now suppose I take a vector V. Okay, so V is just equal V1, V2. Yeah. Then I take AV. So AV will be, you know, A, B, C, D. And then you multiply V1, V2. Right? Then now you multiply it, you know, by just linear algebra, you take AV1 plus BV2, and now you have CV1 plus DV2. Okay, and now you compute the one norm of AV. So remember this one, if the one norm of the vector V, then it just equal V1 absolute value plus V2 absolute value. Okay, So now you got AV, the one norm. It's just absolute value of AV1 plus BV2, right? Absolute value of the first entry plus the second entries, like the absolute value CV1 plus DV2, right? And now, I have triangle inequality, right? So I can take in a triangle inequality, I can take out the absolute values. I got A absolute value times V1 plus B absolute value V2 C absolute value V1 plus the absolute value V2. Okay, so this one by triangle inequality. Okay, agree? Yeah. So now let me do one more thing. Okay. So now let me take. So remember, this is V1, right? So V1 is the common terms here. So V1 is a common term here. So if I take V1 to be the common term, then I got absolute value of A plus absolute value of C. Okay, so maybe this one is still equal. Yeah, it's from here to here equal. And then I do the same. So I got V2, right? Then I got V2, then I got the common term, then I got B plus D here. Great, yeah. So now look at this one. So this quantity and this quantity, I don't know which one is bigger, right? I don't know which one is bigger. Then I just assume that, one of them is bigger. Then I can bound it, like, so I can bound it like to be the common bound. Yeah. So I don't know which one is bigger. So I just write maximal of the two terms. Max of A plus C in absolute value, right? B plus D in absolute value. Then what I left is just V1 absolute value plus V2 absolute value, right? So suppose, this one is A, this one is 10. You take 10 to be the common term, right? Then you can bound like this. So then you got V1 absolute value, V2 absolute value, okay? And now what do I have? So now what I have is, now I just divided. So I take A, V, one norm. So remember, I start from here. I got up to here. I just divided by V1 absolute value plus V2 absolute value. Okay. And less than or equal max of A plus C in absolute value, B plus D. Okay. But this one is nothing but the one norm of V, the one norm of V, remember? So actually this one we can write like AV one norm over V one norm, right? Less than or equal max of A, C, B, D. So everything is absolute value. Yeah. And now you can take a maximal over V. So you take max of on the vector V non-zero of AV one norm over V one norm less than or equal max of A, C, B plus D in absolute value. And by definition, this one is just one norm of the matrix A, and less than or equal max of A plus C, B plus D in absolute value. Okay. So we show that the norm of A in the one norm is less or equal this max of the sum of the columns in absolute value. Okay, it's always less than or equal. And now we just need to show that, in fact, equality can happen. And then we are done. Yeah. So now, how do I show that equality can happen? So I have shown this already. Yeah. So now, in order to show that equality can happen, you just choose a special, so you choose a special V. So suppose so with our loss of generality, yeah, you assume that max. So now assume max of A plus C, B plus D. Assume that the first column gives you the max value. Right? With our loss of generality, you can assume that the first column gives you the max value of the two. Okay. Then now you choose the vector V so that AV is exactly this one. So now how do I choose that? So now if I choose a vector V, say V star, right? So V star, yeah, to be what? I want the absolute value of A. Okay. So maybe vector B. So choose V. So choose V so that when I take AV, yeah, then so maybe this one is V star 1, V star 2, right? So V star 1, V star 2. Then what I want is A V1 plus B, so this star, yeah. So V2 star, C V1 star, D V2 star, right? And I want to choose V1 star and V2 star so that this one, okay, so now choose, yeah, you have to choose. So then when you take the one norm, then it's equal A plus C in absolute value. So what I want is I want to choose so that this one is just equal A and this one is just equal C. So how do I choose that? So how do I choose V? Yeah, so just a unit vectors, yeah, you just choose this one to be 1, 0. Okay. Then this one give you 1 here, 0 here, so let's give you A and C. Yeah. So by choose V star equal 1, 0. Yeah. And then AV star, take the one norm, it just equal A plus C. So you see, so equality occur, right? So you can choose V star so that equality occurs. So therefore, you can conclude that the one norm of the matrix A is equal to max of A plus C, B plus D. Okay, so that is how you prove it. Yeah. So the first step is you show that the first step you have to show that the one norm of A is always less than or equal to the max of the row sums, column sums in absolute value. And the second step is you show that, okay, equality can happen by choosing a special vector V. Yeah. So the full proof for the general case is in the lecture notes, but when you understand the 2x2 cases, the 2x2 case, then you understand the general case. Okay. And then now we go back to the slide. So you see that, remember, this is not a definition of the one norm, okay, but it's just a consequence of the definition. Okay, so you apply the definition, then you apply triangle inequality, you apply the definition of the one norm, definition of the norm of the matrix, then you got out this. The one norm of matrix can be computed by max of the row sum, sorry, the column sums in absolute values. And by the same method, you can show that the infinity norm of a matrix, okay, is the maximum of the row sum in absolute values. Okay, so remember, look at the index here. The index here, you sum over I, right? So sum over I, and that's why you sum over the columns, and then you max, over J. Yeah? This one is in a different order, so max over I, but you sum over J. Okay, so now maybe do a simple example. So now suppose I have a matrix A like this. Then what is the one norm and what is the infinity norm? In exam, will there be a lot of proof questions? So maybe I will post some past exam papers next week, but you got a mix. So there's some calculation question and there's some simple proof questions. So, if you want to get a pass, then you just do the calculation question. And you want to get an HD, then you have to do a lot of proof. So it's up to you. Okay, you can choose. Yeah. So, but we have to distinguish the one that got HD and the one who got a pass. So, okay. So now, how do I compute this one norm of the matrix here? So now let me copy the matrix, yeah, and then I will do a quick calculation. So A is 1, 2, 6, 3, 0, 9, minus 4, minus 1, minus 1. Okay, so now let me show my matrix here. So then the matrix A here, the one norm is just the max of, so now you take the first column, take the sum. So in absolute value, so 1, 2, 6 is 9, and this one is just 12, and this one in absolute value is just 6. So you got 12 here. Okay, and infinity norm, you just take max of, so now you have to take the row, yeah, in absolute value. So 1, 3, 4 is 8, and 2, 0, 1 is 3, and this one is 16, so give you 16. Okay, so any question? Then I have to stop the lectures here because I have a tutorial right after this. So any question? Stop the recording now.